Welcome back to The Explainer. Today, we're basically throwing on our virtual safety goggles and stepping straight into the lab. We are going to examine a group of elements that are as wildly fascinating as they are fiercely volatile, the Group 1A alkali metals. Seriously, get ready, because this virtual tour is going to be pretty explosive. Okay, let's dive into this. When you hear the word metal, you probably picture something, rigid, unyielding, heavy, like steel beams or a cast iron skillet, right? Well, scratch that, because right away we have to subvert those expectations completely. The brilliant chemistry creator Nile Red notes that alkali metals, like sodium, are bizarrely soft. They're actually squishy. You can literally deform them with your bare hands if you squeeze hard enough. They're totally the rebels of the periodic table. So let's introduce our volatile cast of characters here. We've got lithium, sodium, potassium, rubidium, cesium, and finally, the notoriously short-lived, highly radioactive francium. Now, you won't ever find these metals just sitting out in the open in nature or even just chilling on a standard lab bench. Nope. Because they are so incredibly reactive, they actually have to be stored completely submerged in mineral oil or an inert atmosphere just to prevent an absolute disaster. So the crucial point is, why do these elements behave so chaotically? Well, it all comes down to the number one. Every single alkali metal shares exactly one valence electron in its outermost s orbital. Chemically speaking, their atoms are literally desperate to give this one electron away so they can form a stable positive ion. And it's that single, lonely electron that acts as the engine driving every strange, violent reaction we're about to witness today. Experiment 1, the knife test. All right, so imagine we pull these spherical chunks of metal out of their mineral oil baths, pop them right onto a cutting board, and just take a knife to them. If you were standing in the lab right now, pressing a scalpel or a knife into a piece of sodium or potassium, you would immediately feel just how soft and ductile it is. Our lab's standard operating procedures highlight exactly this point. You absolutely don't need a saw. These metals give way under pressure and cut smoothly, literally like a stick of room temperature butter. Now, what's really interesting about this is the incredible visual contrast you get the exact moment you make that cut. When the knife slices through, the interior reveals this stunningly beautiful, brilliant silver luster. But it is incredibly fleeting. Almost immediately upon contact with the air, that gorgeous shiny surface starts to rapidly tarnish. It reacts with atmospheric oxygen to form this ghostly, dull gray layer of oxides all over the outside. And things escalate fast. At 0 seconds, you've got pure silver metal. Within just 10 seconds, the surface is already heavily tarnished gray. But if you let it sit over time, or let's say you're cutting a metal like potassium and you don't keep it absolutely smothered in that mineral oil, it becomes incredibly dangerous. It'll rapidly develop superoxides, generate intense heat right there on the table, and can actually spontaneously combust. It will literally catch fire entirely on its own. Experiment 2, the water drop. Now that we've seen how intensely they react to simple air, let's introduce the alkali metals to a drop of water. This dense chemistry translates into a literal recipe for a localized explosion. Step 1, the metal hits the water. Step 2, a violent reaction immediately kicks off, where the metal displaces hydrogen gas. For the chemistry buffs, the formula is 2M plus 2H2O yields 2MOH plus H2. But it's step 3 that really brings the fireworks. This reaction generates an extreme amount of heat. That heat instantly ignites the newly displaced hydrogen gas, resulting in a fierce, fiery pop. Let's see how this builds. Because as we travel down the Group 1A column, the atomic size actually increases, and the reactivity just skyrockets. Lithium goes first, reacting readily by fizzing and bubbling on the water. Then sodium escalates things. It reacts vigorously with the heat melting it into a literal sphere that frantically darts around the surface of the water. But potassium? Potassium takes no prisoners. It reacts explosively, instantly bursting into brilliant violet flames the absolute millisecond it touches the liquid. Which brings us to a bit of dark laboratory humor that's explicitly outlined in the safety manuals. Say your potassium just exploded and started a fire in the fume hood. Human instinct screams to throw water on it, right? Or maybe grab a standard carbon dioxide fire extinguisher. But if you do that with an alkali metal, you're only going to make it angrier and vastly more violent. They react explosively with water and carbon dioxide. You have to use a specialized powder-based ABC extinguisher to literally smother the flames. Experiment 3. The flame test. Let's pull back from the explosive kinetic energy for just a moment. The physics behind what we are about to see all comes right back to that one chaotic single valence electron. When you place an alkali metal in a flame, the heat excites that lonely electron, bumping it up to a higher energy level. But it can't sustain that state. The moment it falls back down to its ground state, it sheds that extra energy by emitting a brilliant, gorgeous burst of visible light. And this brilliantly illustrates how every single element gives off a specific, characteristic color based on its energy gap. Lithium burns this stunning, vivid crimson red. Sodium creates a blindingly bright golden yellow. Potassium flares a soft lavender lilac. Rubidium glows a deeper lilac. And cesium burns a piercing, bright blue. It is such a stunning visual representation of atomic structure happening in real time. The boss level, the deadly liquid alloy. So we've seen them cut, we've seen them explode, and we've seen them burn. But what happens if you take a chunk of sodium and a chunk of potassium, put them in a dish under kerosene, and literally just squish and rub them together? Fascinatingly, their solid structures deform and break down right into each other, creating NaK, a sodium-potassium alloy. It transforms into a glassy, highly dangerous liquid metal that looks almost like mercury, and miraculously, it stays in a liquid state anywhere from -20 all the way up to 785 degrees Celsius. To really grasp the sheer danger of this liquid metal, just listen to this description from chemistry experimenter Thoisoi 2. Instantly ignite in water, forming burning droplets. If you drop this alloy on the wet surface, the alloy will also light up, sometimes with an explosion. I mean, wow. This alloy demands absolute awe and respect. You're dealing with an incredibly hyperreactive liquid that wants absolutely nothing more than to aggressively oxidize. Which brings us to this massive, kind of mind-blown paradox. This NaK alloy is extremely dangerous, right? It's significantly more active than either the sodium or potassium standing alone. Yet, humanity has somehow found a way to harness this chaos. Because it transfers heat so effectively, this violently explosive liquid metal is actually used practically as a coolant in nuclear reactors. No way, right? We use one of the most reactive substances on Earth to keep our most complex energy systems from melting down. As we wrap up our virtual lab tour today, we're really left with this incredible contradiction. Alkali metals are visually stunning, soft enough to squish with your bare hands, yet chaotic enough to detonate on contact with a single drop of water. And all of it, the explosions, the vivid colored flames, the liquid alloys, is totally dictated by the desperate behavior of one single invisible electron. It really leaves you wondering, if just one tiny atomic particle can wield such immense violent power, what other invisible forces are quietly shaping the massive physical world around us every single day?